Welcome back to the deep dive. Today we are doing something a little different. Usually when we talk about APIs, computers talking to computers, we picture something pretty clean, organized.
Right, like a polite librarian handing you a book,
Yeah.
very orderly.
Exactly. But I'm looking at the opening visual for today's research on gRPC, and orderly is not the word that comes to mind. It looks, well, it looks industrial. We're looking at a diagram of heavy-duty pipes, pressurized valves, binary frames shooting through some kind of mechanical system.
That's actually the perfect mental shift to make right at the start.
Okay.
Because today isn't about the librarian model of the web. Today is about high-performance plumbing for massive distributed systems. We are talking about gRPC.
So the mission is speed.
Speed, scale, and strictness. When you're building something the scale of, say, Netflix or Uber, standard web requests sometimes just don't cut it. You need to strip away the pleasantries and get down to raw efficiency.
Okay, let's establish a baseline then. Most developers know REST. That's the standard, isn't it? You've got this great comparison here, moving from resources to intent. On the REST side, there's a filing cabinet.
Yes. Think of REST like a literal office filing cabinet. It's resource-oriented. Everything is a noun. You've got a user file, a report file, and you use these really generic verbs to handle them. Get, post, delete.
So I walk up and I say, give me the user file.
Exactly. It's passive. You're just exchanging documents. And crucially, those documents are usually text, JSON. You could open them up and actually read them. Name, John Doe.
It's human readable.
Right. But then we look at the gRPC side of this slide, and the filing cabinet is gone. Instead, we have these interlocking gears, pistons. It's labeled action-oriented.
Okay.
Because RPC, which stands for Route Procedure Call, it isn't about fetching a file. It's about triggering an action. It focuses on intent. You aren't saying, here's a representation of the user. You're saying, create user.
Ah, so you're not handing over a document. You're pushing a button that starts a machine.
That is the distinction. REST is, here is some info. RPC is, do this thing.
The notes mention this isn't actually a new idea. It says RPC goes way back to 1958, Fortran second.
Well, history is a circle, right? We're reaching back to the dawn of computing for this.
Mm-hmm.
The idea of calling a function on another computer is ancient in tech years. But gRPC is the modern, cloud-native evolution of it. And unlike that text-based filing cabinet, this machine runs on binary.
So it's not human readable.
Not at all. It's machine efficient.
Okay, so for building a machine, what are the parts? We have an architecture diagram here labeled the magic trio. It seems like gRPC isn't just one thing. It's 3 layers stacked together.
Correct. To get that industrial speed, you need 3 specific components working together.
Yeah.
At the very bottom of the foundation, you have HTTP2.
Hang on, HTTP, isn't that
Yeah.
just the web? Why does the 2 matter so much? I mean, why can't I just use regular HTTP?
That is a huge misconception. Old HTTP 1.1, it's like a one-lane road. You send a request, and all the traffic stops until the response comes back.
Right, it's sequential.
Exactly. If that first car breaks down, you've got a traffic jam. HTTP2 is a superhighway with multiple lanes. It allows for something called multiplexing.
Multiplexing, break that down for us.
It means we can send lots of requests and responses at the same time over the exact same connection without them blocking each other. You can have 100 things happening at once on one wire.
Wow, okay, so we have a superhighway. What's driving on it?
That's the top layer. Protocol buffers, or protobuf. This is the language. It's how we turn our data into that really compact binary format. And then sandwiched in the middle is the gRPC runtime, which is kind of the traffic controller.
The diagram shows the flow here, and it's interesting. It starts at the client application, but it goes down through something called a client stub.
The stub is the magic trick. To you, the developer, the stub just looks like a local function in your code. You just type create user, and it feels like it's happening right there on your machine.
But it's not.
Not at all. The stub takes that command, turns it into binary, shoots it down the HTTP2 highway, and then the server stub unpacks it on the other side.
So it completely hides the fact that I'm crossing a network.
Precisely. It makes the network invisible. But, and this is a big but, for that magic to work, you can't be casual about it. You need very strict rules.
Which brings us to the strict contract. The next slide focuses on the .proto file. I mean, in the REST world, things can be pretty loose, right? I can send you a JSON file with extra fields, and maybe you just ignore them.
Right. We call that sender makes right, or receiver makes right. It's flexible, but it gets messy, If I send you a date in a format you didn't expect, your app might crash.
Or if you rename a field and forget to tell me, everything just breaks.
Exactly. With gRPC, there is no wiggle room. The .proto file is the law. It's the single source of truth. Both the client and the server agree on this contract before a single byte gets sent.
I'm looking at the code snippet for this contract. It defines a message to unary request, and inside it has string content equals 1.
Stop right there. That little eel1, that is the most important part of this whole thing.
I was going to ask about that. That looks weird. I mean, usually in code it's content. Hello, we're assigning a value. Here we're assigning a number to the variable name.
Those are called wire tags. They are permanent identifiers for that field. This is the secret sauce of gRPC speed. When the data actually travels over the wire, gRPC doesn't send the word content, it just sends the number 1.
Wait, so the field name just disappears?
Completely gone.
That's actually brilliant.
It is. Think about a massive JSON file where you're repeating keys over and over and over. Name, John, name, Jane. You're sending the word name 1,000 times. In gRPC, you just send the number for name, say 1,000 times.
But that implies a really serious risk, doesn't it? What if I decide later, you know what, I don't like the number 1, I'll change content to be number 2?
You've just broken the contract. The server will get it too and have absolutely no idea what you're talking about. You have to be disciplined. You can never, ever change those numbers once they are in production.
Let's actually look at what this efficiency looks like. We have a hex dump slide. This is like CSI for data packets. We're analyzing a message that just contains the word hello.
Right. And the whole payload is just 7 bytes. 0A, 05486566C, 66F.
So what are we looking at? Break it down.
The first byte, 0A, that's the tag. It tells the system, this is field number 1, and it's a string. The next one, 05, is the length. The value that's coming is 5 bytes long. And the rest is just the ASCII for HELLO.
No curly braces, no quotes, no colons.
None of the fluff. We've scripted down to the absolute mathematical minimum needed to send that information. It's optimized for the machine, not for your eyes.
But someone still has to write the code. And the next slide shows the code generation pipeline. There's a big gear icon right in the middle labeled proto compiler.
This is the factory floor. You feed your contract .proto file into this compiler, and then out the other side pops your code in whatever language you want. Python, Java, Go, whatever.
It shows Python files coming out, pb2.py and pb2grpc.py, but there's a huge warning label here. Developer rule: treat generated files as build artifacts. Never edit manually.
That is a golden rule of gRPC.
Why, though? I mean, surely I can just tweak a line to fix a bug.
Don't do it.
Yeah.
Seriously.
Yeah.
These files are not your code. They belong to the compiler. The moment you run that compiler again, like say you add a new field to your contract, it completely overwrites those files.
And your manual changes just vanish.
Instantly.
Yeah.
You have to treat this code as read-only. You import it, you use it, but you never, ever touch it.
Okay, hands off the artifacts. Got it. Now, let's talk about what we can actually build with this. We mentioned that HTTP2 highway. Slide 7 calls this the toolkit for RPC types.
Yeah, and this is where gRPC really flexes its muscles over something like REST. In REST, you're usually just stuck with request response. I ask, you answer, that's it. We call that unary.
But here we have server streaming. The visual is a stock ticker.
Right. You send one request, give me the price of Apple, and the server keeps the connection open. It just keeps pushing updates to you. 150, 151, 150.5. You don't have to keep polling asking, what's the price now? What about now?
That saves a ton of overhead.
Yeah.
Then there's client streaming.
Imagine uploading a huge video file. You don't want to send a 2 GB file in one giant request that'll just time out. You stream it in chunks, chunk, and at the very end, the server just says, got it, success.
And the final one, which looks kind of chaotic in a good way, bidirectional streaming.
Live chat or a multiplayer game. I'm sending data, you're sending data, the messages are crossing in midair. Because of that HTTP2 multiplexing we talked about, gRPC handles this totally naturally. It's like a conversation where we can both talk at the same time.
It's impressive flexibility. But because we're treating network calls like they're just local functions, surely there are pitfalls.
Exactly. That's the danger of the stub abstraction. It works so well you forget that the network even exists. And that's why the next slide focuses on resiliency, specifically deadlines.
The code snippet shows context.time remaining. It's checking if there's less than 0.1 seconds left, and if so, it aborts.
This is critical. In a distributed system, if one service hangs, it can cause a chain reaction and take down the whole platform. You have to set strict deadlines. If you don't answer me in 200 milliseconds, I'm hanging up.
You have to be ruthless.
You do, to keep the system healthy.
The slide also mentions rich status codes.
Yeah. In HTTP, every error is just a 500 or a 404. It's so vague. gRPC gives you a specific vocabulary. Invalid argument, deadline exceeded, unauthenticated. It tells the developer exactly why something failed.
Speaking of logic, the next slide introduces middleware logic. Interceptors. I love the visual here. It's a flowchart with a little security guard checkpoint.
Interceptors are so powerful. They sit before your actual business logic. So a request comes in, and it hits the interceptor first. The interceptor can ask, do you have a valid token?
Yeah.
Or have I seen this request before? Is it in my cache?
And if it's in the cache, the interceptor just returns the data right there. It never even bothers the main service.
Exactly. It keeps your core code really clean. You don't want to be writing authentication logic inside every single function. You write it once in an interceptor, and it just applies to everything.
Let's shift gears to how this actually gets used. We're looking at the client perspective. It's being integrated into a Django app to show a weather forecast.
Right. And we see the enriched feed showing the Tokyo weather. But look at the code. There's a flag highlighted there. Wait for ready.
Sure.
The slide calls that a resiliency feature.
It is. Normally, if your client app starts up before the server is ready, what happens? It crashes, connection refused. But with wait for ready true, the client essentially just says, you know what? I'll wait.
Right.
It holds the request until the server comes online.
That makes the whole system so much more robust.
For sure. Especially during restarts or deployments.
Okay, we have to talk about security. Zero trust networking. This sounds intense.
This is MTLS mutual TLS.
Usually I just check for the padlock icon on a website, right? And that
Yeah.
means I trust the server.
That's one-way trust. You trust the bank. But does the bank trust you? In a zero-trust environment, like inside a data center, you assume attackers are already inside the network. So the server says, show me your ID. And the client says, okay, but show me yours. Both sides have to prove their identity.
That sounds incredibly secure. But there's a flashlight on this slide shining on a gRPC server and a big warning label. Risk.
This is reflection. It's a feature that allows tools to ask the server, hey, what functions do you support? What do your messages look like?
So it's like asking the building for a blueprint of all the doors and windows.
Exactly. It's great for debugging while you're developing. But the warning is crystal clear. Do not enable this in production public endpoints, because you're literally handing attackers a map of your entire API.
Keep the flashlight turned off in production. Got it. So we've seen all the cool stuff, but is this for everyone? The next slide gives us the trade-off analysis.
We have to be honest here. The pros are obvious. Performance, strict contracts, polyglot support, meaning your Python service, can talk to your Java service perfectly.
But the cons. The first one is complexity.
Yeah, it's high friction. You can't just hack something together. You need a whole CI/CD pipeline just to manage those .proto files. If you're a small startup, this might actually slow you down.
And there's a warning icon here labeled the Bermuda Triangle of Google DevTools.
Awesome.
Bazel, protobuf, gRPC.
Yeah, anyone who has worked in that stack knows that pain. If you get a version mismatch between your compiler and your runtime, I mean, welcome to error hell, the learning curve is steep.
Plus, browsers don't speak gRPC natively, do they?
No. If you want to use this on a website, you need a proxy called gRPC Web. It works, but it's another moving part you have to manage.
So the final checklist sums it up. When is this a slam dunk?
Internal microservices, what we call east-west traffic server talking to server. If you have high volume, you need low latency, or you're mixing languages, gRPC is pretty much the standard now. Also, mobile apps love it because that tiny binary format saves battery and data.
When should I just stick with my filing cabinet?
If you're building a simple public-facing API for other people to use on the web, just stick to REST. It's easier to debug, everyone knows it, and you can actually read the JSON. Don't over-engineer it.
The slide has a great quote at the bottom. gRPC is an investment in infrastructure that pays dividends in scale and reliability.
That really sums it up. It costs more upfront, but it pays off when you hit that massive scale.
We're wrapping up with the toolkit slide. Just a quick mention of the tools that make this bearable. We know Protopec, the compiler. What about a grip curl?
Grip curl is essential. Since you can't just look at the binary data, you need a tool to translate it. It acts like CRL, but for gRPC. It lets you test your endpoints right from the command line.
And buff. That's a newer one.
Buff is a lifesaver. It's a modern tool that lints your .proto files. It will yell at you if you try to change a field number and break the contract. It basically stops you from shooting yourself in the foot.
So, looking back at all of this, from the gears to the contracts, what's the big takeaway?
I think it's the shift in mindset. We're moving away from data that's convenient for humans to read toward data that's efficient for machines to process. And it requires discipline. You know, you have to respect the contract. You can't just wing it like you sometimes can with JSON.
Right.
But in a world where systems are getting more massive and more distributed, that discipline is exactly what keeps the whole thing from falling apart.
It's the difference between a casual chat and a synchronized swimming routine. One is flexible, the other is high performance.
That's actually a really good analogy.
I have my moments. So, listeners, think about your own APIs. Are you building filing cabinets? Or are you building gear systems?
And if you are building gear systems, make sure you oil them with a good .proto file.
I want to leave you with a thought to mull over. We talked about how gRPC strips out all the human-readable parts to optimize for machines. If we're moving toward a world where AI agents are talking to other AI agents at incredible speeds to get things done, does human-readable text like JSON become obsolete? Are we building a language for machines to speak to machines and, in the process, excluding humans entirely from the conversation?
That is a scary and very efficient thought.
Thanks for listening to The Deep Dive. Catch you on the next one.